How's it going, everyone? It's Greg. I'm sorry I couldn't be there this week. I'm actually back in New York City doing some shadowing for a potential job opportunity. But anyways, I recorded my presentation. Uh, so yeah, I'll try not to make this too long as I know you guys have a lot to get through today. So yeah, let's get started. I decided to do for my project a classifier of which NBA teams would make the playoffs in a given year. So I chose to do something sports related because I've always been a huge sports fan, and around the time we were coming up with what we wanted our projects to be, the NBA season was winding down, and I just thought if we could choose our project to be on anything, like why wouldn't I do something I'm interested in? So I decided to do a playoff classifier because many teams in the NBA consider making the playoffs a successful year, obviously depending on the team, and then winning the championship is the end goal of every team in the league. So I decided to create an NBA team classifier that would predict whether a team would make the playoffs, miss the playoffs, or win the championship based on their regular season offensive and defensive statistics. So the data I collected from 1979 to last year, and the data is each team's per game offensive and defensive statistics. The data was collected from Basketball Reference, which is, if any of you are sports fans and you've ever used this site before, which I have, it's a great site. Very complete and accurate records. And then the data consists of such stats such as total points per game, assists per game, turnovers, etc. So the data processing, as we all know, we must prepare the data for our machine learning approaches. So first I removed outliers from the data set, and then I formatted the data correctly by removing strings, combined a couple data sets together. Fortunately, Basketball Reference is quite good, as I was saying, so the data was complete, had no missing values. I removed some features that I believe to be less useful in the classification. And then what I did was I had to research and record because there was no actual just like which teams had made the playoffs data set. So I had to go year by year and record which teams made the playoffs, which teams won the championship, and which teams did not for all the years, which took way too long. And then I added a playoff variable for classification that was set to 0 if a team did not make the playoffs, a 1 if the team made the playoffs, and a 2 if the team won the championship. So moving on to the experimental plan overview, I decided to use 3 machine learning approaches. I know we were only required to use 2 if we were working individually, but I figured once I had all the data formatted and set up correctly that it wouldn't take too much time to run a third algorithm for classification just to compare between them. So I chose support vector machines, the infamous multi-layer perceptron, and k-nearest neighbors. So yeah, I wanted to see which algorithm would perform the best. I was leaning towards thinking that SVM and nearest neighbors would do slightly better than MLP, given the nature of this data set and the fact that they have fewer parameters to set and change during testing, and the fact that MLP has many parameters. Yeah, so when I was running MLP, as you'll see, I tried changing a few of the parameters, and I ran the classifier 20 times per test, taking the average of the accuracies, since there's randomness, so you get a different accuracy every time, as you guys know. So yeah. So the experimental plan for SVM, again, since there are a few parameters, I decided to do a comparison amongst the kernels. I ran the classifier with 3 of the 4 possible kernels, RBF, linear, and sigmoid, to see which would perform the best. Max iterations were 1,000. So for the experimental plan for the multi-layer perceptron, there's many parameters to set, as you all know. I decided to run the classifier to see how changing a few of them would impact the performance in the accuracies. I chose to investigate momentum, the learning rate, and how adjusting the size of the hidden layers would impact accuracy. I chose these because these are things we've done throughout the year, so I figured that why not apply that to the project. And so running the test without changing any of the default parameters, so just like, you know, not changing anything, was yielding about a 60% accuracy, which as you'll see is lower than some of the other methods within the MLP, and definitely lower than, spoiler alert, definitely lower than the SVM and k-nearest neighbors algorithms. So here's the MLP parameter table, just an overview of what I was changing throughout my trials, as you can see. I decided to do hidden layers size 36 just because that was how many features were in the data set. I just messed around with and then learning rate and momentum a little bit just to see how that affected the performance. So for the k-nearest neighbor, like SVM, this approach has few parameters. The only real parameter to be set is k. I also decided, just to test something else, that to set the weights equal to both uniform and distance, which when they're equal to uniform, they treat all points equally, or you can set it to distance, which weights points closer in distance more heavily, to see if that had any effect in the accuracy. And so there's the parameter table for the k-nearest neighbors. I went with just some random amounts of nearest neighbors, and then changing the weights from uniform to distance. So now moving on to the results from some of the testing. First up, the k-nearest neighbors results, as you can see here, increasing the number of nearest neighbors, or the number of k, seemed to improve accuracy in both the uniform and distance settings, and the highest accuracy achieved was when k was set to 40 and the weights were set to uniform, just over 77%, which I think is fairly high. So this algorithm performed fairly well. Here's just a graph of the accuracy by increasing k. So you have k on the x-axis, accuracy on the y-axis. As you can see, it hits the peak, as we saw in the previous table, peak at 40. And then there was a decline after 40, which I thought was interesting. The decline did continue for numbers higher than 50. I just didn't include them in the graph, but I saw that when I was testing it. And this is when the weights were set to uniform. And here's a graph when the weights were set to distance, a pretty similar shape. There's the same peak at 40 and decreasing afterwards. I'll build up before 40, obviously. And moving on to the SVM results. So I tested linear RBF in the sigmoid kernels, as I said previously, and the highest accuracy, which was achieved by the linear kernel. The accuracy was 76.55%, which is pretty close to the top accuracy of the k-nearest neighbor algorithm. And I think, if we recall the assignment we did during the year, that linear was also the best performing, and then sigmoid was the worst performing here, and as well in the assignment as we did. So I thought that was interesting. Here's just a simple graph of the kernel accuracy comparison. And finally, the MLP results. So as you can see, the same table as I had from before, the different parameters, and now just adding in the accuracies they achieved. So the MLP was actually the worst performing algorithm from my testing, and it achieved the highest accuracy out of all the trials, was 65.766%, the last row here. As you'll see from the graphs on the next couple slides, changing the learning rate or the momentum didn't really improve accuracy at all. The only thing that seemed to give a slight bump to the accuracy was increasing the hidden layer sizes, or increasing the number of hidden layers. So yeah, just looking at the momentums, I mean, they're all over the place, regardless of what they're set to. So you can't really draw any conclusions about higher momentum improves the accuracy in this case. Moving on to the learning rate. Again, similar to momentum, the standard learning rate of 0.001 seemed to be, the blue line up there seemed to be on top for most of the time. But you can't really say for sure which of these perform the best, other than green performed the worst. Then we have the hidden layer sizes. So the hidden layer where it was set to 36 nodes and 3 layers, the red line seemed to perform the best as it's on top. Most of the time that was the setup that actually had the highest accuracy, so we could see that. And the blue line, where it was just 1 layer and 36 nodes, seemed to perform the worst, the blue line, as you could see. So anyway, just to briefly summarize the results that you guys just looked at, it is clear that both the SVM and k-nearest neighbors far outperformed the MLP in this test. The achieved accuracy is almost over 10% higher. The MLP performing worse, I think could be due to my error not setting the optimal parameters, as there are many to set, and it could be the case I'm not setting them correctly, or just that MLP isn't optimal for this data set. I'm not really sure. But anyways, the top performing approach was the k-nearest neighbors with k equal to 40, and the weights equal to uniform, which achieved 77% accuracy, which I think is fairly acceptable. As far as improvements, I think doing some more feature engineering definitely could have been beneficial to the outcome if I looked into that more. But overall, the results were fairly acceptable in my opinion. Now, as far as ethical concerns, I don't think there are too many that go into the analysis I did. The only one I could really think of, it's been a hot topic if any of you are sports fans or NBA fans, is the NBA has, there's the rising concern about teams tanking, which, if you don't know what that is, they pretty much the team will lose on purpose for a season, because if you lose, you have a better chance to get a high draft pick as well as other assets. So there are questions about whether this is moral or not, considering the NBA advertises itself as a competitive league. If you buy a ticket, if you're a fan, you buy a ticket for one of the teams tanking, are they really selling you the product you're buying? Even if you're a fan of another team and you go to a game and they're playing a team that's trying to tank, it's not going to be a competitive game. Are you really getting what you paid for? There's fans of these teams that buy tickets and other merchandise. Is it fair to the fans for these teams to lose on purpose? And so, if it could be proven that teams that tank have a higher percentage of chance of making the playoffs in the coming years, this could be justification for more teams to tank and more problems to occur. Perfect example was the 76ers last night. They actually knocked off the Miami Heat to make it to the next round of the playoffs, and this was pretty much the strategy they were, very blatantly taking on. They tanked for 3 to 4 years, and they got very high draft picks, and now they're very good. So it'll be interesting to see if this is a trend that continues. But yeah, it's definitely an ethical concern regarding the NBA and how teams perform. So just for conclusions, I'm fairly happy with how the project turned out. I think the classifiers were able to somewhat accurately predict correctly. Obviously, I am not the best at this, so I think improvements can be made in both the feature engineering and parameter setting stages. I also think one thing that I considered along the way was to include individual player data in the analysis, just to see if that would add any improvements to the accuracy. Alright, well, thank you guys for listening. That was my project. We'll see you guys all at the final next week. I hope you have a great week.